We're now going to turn our attention to a concept known as chemical kinetics. This information in Chem 2A is found in Chapter 10, Section 10.1. Chemical kinetics is the study of the rate or the speed at which reactions proceed. How fast is a reaction going? Notice that as we study kinetics, it gives us information that enables us to either speed up reactions that we want to happen, in other words, speed up desirable reactions, or alternatively, maybe we don't want this reaction to happen, it's an undesirable reaction, and we want to slow it down. So studying reaction rates, how fast a reaction is going to enable us to gain the tools we need to speed up the reactions we want to have happen and slow down the reactions or processes that we don't want to happen. Now, in order to understand kinetics further, we have to discuss collision theory briefly. And collision theory is a model which explains the conditions that are required for a chemical reaction to occur. The collision theory proposes that in order for a reaction to occur, molecules must collide together. And what this does is allow energy transfers to occur between molecules to provide the energy needed to break the bonds in the reactant molecules. They first of all have to break the bonds that are holding the atoms that make up the reactant molecules together so that those atoms can rearrange and form new bonds in the products. So colliding together allows energy transfers to occur because in order to break a bond, energy has to be supplied. The second thing that is proposed in the collision theory is that molecules must collide in the proper orientation. And this orientation or alignment positions the proper bonds to break in the reactants so that new bonds can form in the products. And lastly, molecules must collide with sufficient energy. And again, energy is critical in order to break bonds in reactants and form products. And this diagram below is going to amplify that. So molecules can collide together, but if they collide together with insufficient energy, they'll just bounce apart and without reacting to form product. So it will be an ineffective collision because it lacked sufficient energy needed for the bonds to break in the reactants. Right, so to get a better understanding of energy requirements, let's take a look at a potential energy diagram and introduce a concept known as activation energy. So I've drawn a potential energy diagram, right? We saw this diagram illustrated when we were looking at endothermic and exothermic reactions. And this diagram is a potential energy diagram for an exothermic reaction, which we can immediately recognize as exothermic because on this graph, with potential energy shown on the y-axis and time on the x-axis, we see that the products are at a lower energy state than the reactants. So as this reaction proceeds forward, the reactants are losing energy to make products, and that is an exothermic reaction. So we're going to introduce the concept of activation energy, illustrating it with the potential energy diagram for an exothermic reaction. Notice what the potential energy diagram is saying, that before reactants can form products and go to a lower energy state in the process, they actually have to pass through a higher energy state known as the transition state. So reactants don't just immediately, boom, form product without passing through what is called the transition state. The transition state is a short-lived, high-energy chemical species, right? So it's a chemical species, very unstable, very high energy, very short-lived. So notice the transition state is the highest structure on the potential energy diagram that is indicated. It is always higher in energy than either the reactant or the products themselves. So a short-lived, high-energy, very unstable chemical species that has a bonding structure in between or intermediate between the reactant and product structures. So you wouldn't even want to try to draw a standard Lewis dot structure for a transition state species because the bonding would be very unusual, very weird. You wouldn't expect the octet rule to be followed. It's not a stable structure. That explains its high energy and short-lived state. So in order for reactants to form product, they first must achieve this transition state, this high energy structure. Notice that I have an arrow pointing from where the reactants are at in terms of their potential energy all the way up to the transition state. And this arrow that I'm referring to is called the activation energy. And it's abbreviated with a capital E and a subscript A. The activation energy is the energy that must be gained by the reactant molecules to achieve the transition state. So reactants are going to have to gain or absorb the activation energy needed to form the transition state and then move on and become the product structures. So all of a sudden, the collision theory is making more sense. We understand why molecules have to collide with sufficient energy. If they don't have sufficient energy, then they may start to climb this activation energy barrier, but then fall right back into the reactant structure. It's insufficient energy to achieve the transition state in many collisions. Only some collisions possess sufficient energy to go all the way up the activation energy hill and form the transition state. So having explained what activation energy is, we can now discuss another concept, and that is what effect does a catalyst have on a reaction? So a catalyst is a substance that speeds up the rate of the reaction. So catalyst, all right, acts to speed up reaction rates. It's usually a substance, but it can also be something like light energy that acts to cause the reaction rate to speed up. But normally we're looking at some chemical substance, right? The catalyst is neither the reactant nor the product. So you would never try to consider the catalyst as either a reactant or a product. It always appears over the reaction arrow to say that its job is to simply speed up the reaction rate without itself being permanently changed, altered, or consumed. How does a catalyst do its job? Right? So how does it work? Here's what the catalyst is doing. The catalyst is providing, let me make this line black again. The catalyst is providing an alternate pathway for the reaction to proceed, right? So the catalyst is providing an alternate pathway for the reaction to proceed. Provides an alternate path for reaction to proceed. And let's make that a little cleaner here. To proceed. There is a new transition state. This new transition state is lower in energy. So a new transition state, and this new transition state is lower in energy. Therefore, right, the catalyst lowers the energy of activation needed for the reaction to proceed. The catalyst lowers the energy of activation needed for the reaction to proceed. And we can maybe put an arrow here and say this is the new energy of activation for the catalyzed reaction. And we see that this new energy of activation in the presence of the catalyst is lower than the energy of activation for the uncatalyzed reaction. So the reaction speeds up as a result of the presence of the catalyst. The last thing that I would want to mention in this potential energy diagram is what we talked about when we refer to the reaction being exothermic. So energy is going to be released by this reaction as it proceeds. That energy that is released is known as delta H, the heat of reaction. And because this is an exothermic reaction, energy is released. We could measure the energy content here of reactants and products and plot them, right? And we know that the difference, the delta H, is going to have a negative sign associated with its value, meaning that it is an exothermic reaction. So just tying in what we learned previously about exothermic and endothermic reactions and indicating this here on this graph.